Hi everyone, this is going to be a review of Heapsort. So let's begin by discussing the algorithm. At a high level, all that we do in Heapsort is we have a given array. We take this array and we make it into a heap, okay? Then we take this heap and then we continually remove or pluck elements from the top of the heap and we place them in a sorted array, okay? So we're basically just using a heap to sort the list. How exactly, though, is this process working, right? The first step, recall, is that we have an array and we want to make this array into a heap. So there are many ways of achieving this. The most efficient process of taking an array and making it into a heap is called bottom-up heapification. And when we talk about the heap that we're creating, in Heapsort, we're going to be creating a max heap. And this may seem a bit weird because in this class, we've been talking a lot about min heaps, but Max Heap is actually a bit better than a min heap for Heapsort, and we'll soon see why that is the case in step 2. But until then, let's try to figure out or try to understand how this process of bottom-up heapification works. So the first step here is we have this given array, and we want to visualize this array as a heap. So what we can do is we can take all the elements in this array and put them in a heap in level order. Okay, so all I've done here is I've taken all the elements from this array and I've put them in this heap in level order. Okay, now what we're going to do is we're going to take this heap and we're going to convert it into a max heap, right? How we're going to do that is we're going to start from the end of this array or the last element in the heap, and we're going to bubble that down. And then we're going to move on to the second to last one and bubble that down, and so on, until we get all the way to 7. Okay, so notice that for all of these 4 elements, when we bubble them down, nothing really happens, okay? Then when we bubble down 4, notice that 4 is greater than 2, so nothing really happens when we bubble down 4, okay? Then when we get to 9, notice that 9 is greater than its children, so we keep 9 where it is, right? Finally, when we get to 1, now we have some work to do because 4, which is a child of 1, is bigger than 1. So let's bubble down 1 and swap it with 4. Okay, now we have this state, and then what we're going to do is swap 2 and 1. Okay, so the last thing we need to do here is bubble down 7, and how we're going to do that is swap it with 9. Perfect. So after the following steps, what we've noticed is we've taken this heap and we've converted it into a max heap, right? Because we can see that this heap over here is a max heap. So the next step in the algorithm is to take this max heap and continually remove the maximum item and put that maximum item at the end of the array, okay? So all that we're doing is that we have, let me move down this heap that we've created. We're going to keep removing the maximum, which is at the top, and putting that maximum at the end, okay? And every time we remove the maximum, we have to do the usual process of taking the last person, promoting that last person to the top, and then bubbling that last person down, right? Okay, so let's kind of see this in action. And this is why a max heap works really well. So this is the same state as from up here, okay? The first thing that we're going to do is we're going to remove, oops, this should be remove max. I think I wrote that in a couple places. So we're going to remove max and swap 9 and 1, okay? So what's going to happen here, which is really cool, is that when we remove 9, we're going to put 9 at the end of this array. And now what's cool is that the beginning of this array is the current state of the heap, right? since we lost an element in the heap. And this is really good because now the vacant spot in the array is where 9 goes, right? So that's why using a max heap is really good. So just to summarize once more, that when we use a max heap, when I remove an element from the top, right, now the size of my array is 1 smaller. So it makes a ton of sense to take that element I removed and put it in that vacant spot that was just created. Okay, so in essence, what we can think about when we run heap sort is that we're growing a sorted array from the right-hand side of the array. Okay, so jumping back to this example, we promoted 1 to the top, right? Now what we need to do is bubble down 1 so that we preserve the property of the max heap. Okay, so let's kind of move this down and then let's walk through that process. Okay, so we take 1, we're going to switch it with 7, and then we're going to switch it with 6. Perfect. Okay, so now what we can see is that this is our current state of the max heap, and that's the exact same as what's here, right? 4, 6, 2. Okay, perfect. So the next step here is that we want to repeat this process. Let's just do one more iteration of the algorithm just so we drive it home. Okay, so what's going to happen here is that we're going to swap 7 and 1. Okay, because 7 is the new maximum. How that's going to look is that 7 is going to go in this spot, but it's basically eliminated from the heap, right? And we're going to move 1 again to the top. Sadly, 1 keeps getting promoted to the top. But then what we'll notice is that now we've solidified 9 and 7's location in the final sorted array, right? But we still have to bubble down 1 to preserve the max heap property. So let's see that in action. We'll see that it becomes 6, and then 5, and then 1. Okay, perfect. Well, that is the heap sort process. If we keep repeating this, eventually this sorted array here will encompass the entire array. Okay, so let's kind of think about the best and worst case runtime of heap sort. And I think this is really important. So when we think about the overall runtime, we can break it up into 2 parts, okay? The first part is heapifying the array. Okay, this is part 1. And the second part is the bubble down operations. Okay, this is part 2. So if we figure out the runtimes of each of these parts, we can figure out the total runtime. So it turns out that bottom-up heapification, which is this first step, takes us theta of n time, right? And this may seem like a little weird because like how is it theta of n? Usually if we like do n bubble downs, it should be n log n. But there's like kind of a clever nature in how bottom-up heapification works. So it turned out to be theta n. But the proof of why it is theta n is not in scope for CS61B. Okay, so when we look at the bubble down operations, this comes out to theta of n log n. Because we bubble down n elements, and each one goes for log n, right? Okay, so what we will notice here is that the worst case is n log n, right? But the best case appears to be theta of n. And this is really an edge case of a situation. And it's when all the elements are duplicates. In this situation, usually when we bubble down, it takes us log n time. But if the elements in the heap are all duplicates, bubbling down takes constant time, right? In this case, this becomes theta of n. And then the overall runtime is theta of n, okay? But the worst case here is more important than the best case. So let's think about why would we use heap sort? Well, it has a good worst case bound, right? Theta of n log n is so far the best out of all the algorithms I've walked through. And another good idea is that it's good if we're given a heap, right? It may seem kind of silly, but sometimes we're given a heap. And another benefit of heap sort is that it's in place. But we'll soon see that other sorting algorithms of the same runtime tend to be a bit better and more used in practice. So for a quick understanding question before we conclude this video, suppose that we have a magical max heap that has a constant time for bubble down. How would the worst case runtime change if at all? Okay, so at this point, pause the video, try to figure out how the worst case runtime of Heapsort changes, and I'll be going over it in a couple seconds. Okay, perfect. So recall that we can think about the runtime in these two components, okay? So if bubble down took constant time, then what we'll notice is that this becomes theta of m time, and then the beginning was already theta of n time. So the worst case runtime improves the theta of n. And this question may seem a bit silly, but it's important to understand why the runtime of these sorting algorithms is the way it is. Because in an exam, a common problem we like to ask is, let's say I decide to tweak this algorithm like so. How will the runtime change, right? So yeah, hopefully I'll enjoy this video and stay tuned for the next one.